High-performance digital signal processors are the need of the hour in today's world. MAC units being integral parts of such processors are desired to consume low power and to operate at high speeds. In this paper, a detailed analysis of MAC units constructed using 4 different types of multipliers, namely Booth, Wallace tree, array, and Vedic, is carried out. Carry save adder, PIPO shift register are used as the adder and the accumulator in the MAC unit. Analyzing the performance of MAC units constructed using different multipliers can help identify the optimum unit to be used in the DSP processors. These designs are constructed for 3 different bit lengths, 4, 8, and 16, and are compared in terms of power consumption, the delay incurred, and FPGA utilization parameters like LUTs, nets, and leaf cells. These designs are analyzed and simulated using the Xilinx Vivatu tool and implemented on Z-board ZYNQ7000 Evaluation and Development Kit, XC7Z020CLG484-1. Keywords: MAC unit, multiply accumulate, Booth's algorithm. Array multiply, Vedic multiplication, Wallace tree, DSP. Processors, carry save adder. Introduction. Recent advances in communication and multimedia systems have resulted in a demand for efficient and fast digital signal processing systems. DSP systems and algorithms are used for processing data streams almost everywhere, and therefore they require high precision and timing accuracy. High-performance digital signal processors consume very low power while operating at high speeds. Filtering, convolution, polynomial evaluation, and dot matrix operations are some of the processes involved in processing signals digitally. These operations usually involve multiplication and addition and are performed by the multiply and accumulate, MAC, unit. The MAC unit is an integral part of all digital signal processors. Fast Fourier transform, FFT, and DTFT require a large number of multiplication and addition operations. The performance of the processor depends largely on the MAC unit. The area occupancy, power consumption, and delay incurred in the MAC unit can influence the overall performance of the system. A MAC unit consists of an adder, a multiplier, and an accumulator. In general, the delay incurred in DSP systems is mainly due to long multiplication processes in the multiplier. A wide variety of multipliers are known to be in existence. Each multiplier has a unique structure and follows a unique algorithm. Vedic, Booth, array and Wallace tree multipliers are some of the multipliers that are being widely used. Analyzing and comparing these multipliers based on power consumption, the delay incurred and area occupancy can help identify the optimum multiplier to be used in the MAC unit. In 1, various multiplication hardware realizations have been presented along with a detailed description of parameters to be considered while designing any digital system. A revolutionary multiplication technique for signed binary numbers has been proposed in 2. This technique, widely called Booth's multiplication algorithm, is independent of any foreknowledge about the signs of these numbers. In 3, a MAC unit was designed using the Booth multiplier and ripple carry adder. The MAC unit coded in VHDL was analyzed, synthesized, and simulated using Xilinx ISE design suite. In 4, Radix 8 Booth multiplier has been designed for signed and unsigned numbers using Verilog. The multiplier has been implemented in Spartan 3 kit. The Wallace tree multiplier has been designed, implemented, and analyzed in terms of speed and equipment cost in 5. The multiplier has adopted an algorithm which reduces the number of summands and accelerates the formation and addition of summands. In 6, the Wallace tree multiplier is compared with the array multiplier, and it is shown that the Wallace multiplier outperforms the latter in terms of speed and power consumption. In 7, a 32-bit MAC using the Wallace tree multiplier was implemented on the Spartan XC3S5004FG320 device and synthesized using 90nm technology using Synopsys Design Compiler, and its results were compared with the conventional MAC unit. A 32-bit MAC unit using a Vedic multiplier and carry save adder was proposed in 8. The delay incurred, utilization, and the number of LUTs required were compared with existing designs. In 9, the procedure for multiplication using Vedic mathematics is proposed and the results show that the time complexity involved is lesser than the conventional ways of multiplication. The delay power performance of various multipliers like Booth, Wallace tree, and Vedic are compared in 10. The implementation of these circuits in VLSI design is also described. In 11, the use of reversible logic gates in the design of the arithmetic logic unit is elucidated. Furthermore, a detailed description of various reversible logic gates like Paris, Feynman, DKG, etc., is provided. A comparison between 64-bit MAC units constructed using Vedic and Wallace tree multipliers is provided in 12. In 13, the array multiplier has been designed and implemented using different adder designs in Cadence Design Suite at 180 nm technology. In 14, the array multiplier has been designed without any truncation or addition technique. Parameters like silicon area, delay, and power have been analyzed for 8, 16 and 32-bit versions. Section 2 provides information regarding the basic components of a MAC unit and the types of multipliers used in this paper. The RTL schematics of all the designs is presented under Section 3. Simulation results obtained from Xilinx Vivatu tool is provided under Section 4. The comparison between the designs in terms of delay, power consumption, and FPGA utilization parameters is also presented there. The conclusion is presented as Section V. 2 components of a MAC unit. A MAC unit consists of 3 components, a multiplier, an adder, and an accumulator. Words are obtained from memory locations and passed as inputs to the multiplier. The block diagram of a n-bit MAC unit is shown in a adder. The adder computes the sum of the product from the multiplier and the value stored in the accumulator. The output of the adder is passed on to the accumulator. If inputs to the multiplier are of bit size n, then the adder should be of bit size 2n, producing an output of size 2n plus 1. Carry save adder, carry select adder, ripple carry adder, RCA, carry look ahead adder, CLA, are among the widely used adders in the design of digital logic processing devices. Propagation delay and critical delay are 2 important parameters to be considered while using adders. In this paper, carry save adder is used in the design of MAC unit. It works on the principle of preserving carries until the end. It is one of the widely used circuits for implementing fast arithmetic computations. As the numbers become large, the propagation delay incurred in ripple carry adder, RCA, and carry look ahead, CLA, adder also increases. Hence, the carry save adder is much faster than conventional adders. The block diagram of a 4-bit carry save adder is shown in Fig 2. Fig 2, block diagram of a 4-bit carry save adder. B. Accumulator. The accumulator is a register which stores the sum of products. It is widely used in arithmetic logic units, ALU, and MAC units. Storing values in the accumulator can eliminate the need for additional summing operations. The response of the accumulator should be fast enough to match with fast adders. Parallel in parallel out, PIPO, shift registers are widely used as accumulators as they are fast and output of given within a single clock pulse. The accumulator used in this paper is a parallel in the parallel out shift register. It is the simplest of all the 4 configurations of shift registers. Both data loading and data retrieval occur in parallel in a single clock pulse. Hence it serves as the ideal choice for an accumulator. The block diagram of 4-bit PIPO shift register implemented using D flip-flop is shown in C. Multiplier. Multipliers play crucial parts in today's digital signal processing systems and various other applications. Using a high-performance multiplier can boost the performance of the entire system. It is desired to have a multiplier with the following characteristics. It should be accurate. It should be able to carry out operations at a very high speed. It should use a fewer number of slices and LUTs. It should consume less power. The process of multiplication involves 3 steps: partial product generation, partial product reduction, and final addition. There is a wide variety of multipliers. Some of them are array, Booth, modified Booth, Wallace tree, sequential, Vedic, and data multipliers. In this paper, Booth, Wallace tree, array, and Vedic multipliers are used in the design of Mac unit. 1. Booth multiplier. Booth multiplier follows Booth's multiplication algorithm invented by Andrew Donald Booth in 1950. It multiplies 2 signed binary numbers in 2's complement notation while preserving the sign of the result. It outperforms earlier methods of multiplication by reducing the number of iteration steps. It schemes the multiplier operand and skips chains of the algorithm, thus reducing the number of additions required to produce the result. 2. Wallace tree multiplier. It is an efficient hardware circuit designed to achieve higher speeds of operation. It was designed by Chris Wallace in 1964. It is a variant of the long multiplication method. Wallace tree reduces the number of partial products and uses carry select adder for the addition of partial products. Here, the total delay incurred is proportional to the logarithm of the length of the multiplier operand. This in turn results in faster computations. The Wallace tree method of multiplication has 3 steps. Each bit of the input is multiplied with each bit of the other input. The number of partial products are reduced by half by using half and full adders. The wires in the 2 inputs are grouped together and then added. 3. Array multiplier. Array multiplier functions based on the add-shift algorithm. It multiplies 2 binary numbers by using an array of half and full adders. Add and shift operations are simultaneously executed while checking the bits of the multiplier followed by the addition of partial products. This multiplier has a systematic and regular structure. However, when compared with other multipliers, it consumes larger power and suffers from long delays. 4. Vedic multiplier. This multiplier is based on Urdhva Triakbhyam Sutra, which is the most efficient one in terms of speed among the 16 sutras. Hence, it is also referred to as UT multiplier. The Urdhva Triakbhyam Sutra applies to both division and multiplication. By incorporating the UT formula in the design of multipliers, high-speed digital systems can be designed. Partial product generation and addition are done concurrently. This results in the reduction of delays incurred. Vedic multipliers of larger sizes can be constructed by duplicating 2x2 Vedic multipliers and adding the products using a ripple carry adder. This is shown in Fig 5, where a 4x4 Vedic multiplier is constructed by using 2x2 Vedic multipliers and ripple carry adders. Using reversible logic gates like Paris, Feynman, DKG in the design can further aid in the reduction of power consumption. An implementation of a 2x2 Vedic multiplier using Paris and Feynman reversible gates is shown in Fig 4. V. Conclusion. In this paper, the multiply accumulate unit is designed using 4 different multipliers in Verilog HDL, simulated and synthesized in Xilinx Vivatu. These designs are compared in terms of delay incurred, power consumption and FPGA utilization parameters. It is seen that Mac units designed using Vedic and Wallace tree multipliers have smaller delays and thus operate at higher speeds. The Mac unit designed using Vedic multiplier consumes the least dynamic power of all the other designs, however it requires the largest number of lookup tables. Furthermore, it can be seen that it requires the least number of nets and leaf cells. Thus, Vedic multiplier designed using Urdhva Sutra is a better choice among Booth, Wallace tree, and array multipliers. 117. 13. 115. 10. 116. 12. 112. 8. 0. 20. 40. 60. 80. 100. 120. 140. Total on-chip power. Dynamic power. Power consumption in MW. Comparison of total on-chip power and dynamic power. Design 1. Design 2. Design 3. Design 4. 3.812. 6.9625. 14.969. 2.9175. 6.132. 12.7931. 9.567. 19.896. 36.493. 2.9497. 5.8945. 11.799. 0. 5. 10. 15. 20. 25. 30. 35. 40. 4-bit. 8-bit. 16-bit. Delay in NS. Comparison of delay. Design 1. Design 2. Design 3. Design 4. 165. 88. 398. 133. 67. 482. 230. 113. 272. 133. 67. 545. 0. 200. 400. 600. Nets. Leaf cells. LUTs. Comparison of nets, leaf cells and LUTs required. Design 1. Design 2. Design 3. Design 4.